In this video, we're going to be talking about areas and distance. In previous math classes, we have been given formulas to calculate the area of various shapes like circles, rectangles, triangles, trapezoids, etc. The motivation for us in this section is to think about how we might find the areas of shapes that are not ones we have simple formulas for. Let's fill out the table below. So the area of a rectangle is equal to base times height. The area of a square is equal to one of its side lengths squared. The area of a trapezoid is 1/2 base 1 plus base 2 times the height of the trapezoid. The area of a triangle is 1/2 its base times height. The area of a parallelogram is base times height. And then the area of a circle is pi r squared, where r is the radius of the circle. Example 1 says, place your wrist on the x-axis and lay the rest of your hand down so that all of your fingers fit within the bounds of quadrant 1. Draw an outline around your hand, then estimate the area of your hand print. Include units. So it was difficult for me to place my hand on my tablet because it covers most of the screen. So I went ahead and I just drew what I think a hand looks like in freeform. And I also drew a hand turkey, and his name is Oliver, and I gave him a top hat. But anyway, so what we want to do is we want to estimate the area of this, and we want to make sure we include units. And so there are tons of different ways we could go about this, but I want to include squares within my handprint, and I am taking a ruler, and so the dimensions of this square are 1 centimeter by 1 centimeter, which means that the area of this individual square is 1 centimeter squared, because I'm multiplying 1 centimeter times 1 centimeter. So area we measure in square units. And so I want to go ahead and do this, and I want to estimate the area of my hand. So that's going to become harder in places where I can't really put a 1 centimeter square. So just do your best to estimate it and then put your final answer in this box here. Our next example says Mr. Kwan runs on the treadmill to prepare for his next half marathon so that he doesn't look like a dying cow at the finish line again. A velocity graph is shown below. Part A says, for what amount of time did Mr. Kwan run? Well, if we notice here, our graph is just giving us a horizontal line, and we're measuring our velocity here in miles per hour. So our horizontal axis is the time, and there's no breaks in our horizontal line, which means we have a continuous function here. So the amount of time that he runs is for 3 hours, because our graph stops at 3 and it starts at time 0 here. Part B says, how far did Mr. Kwan run? So I know that for my velocity, I was traveling 6 miles per hour during my entire run on the treadmill, and continuously I was running for 3 hours. We gathered that from part A of this question. So if I am running at a constant velocity of 6 miles per hour and I ran for 3 hours, for part B, I could take my speed or velocity, 6 miles per hour, and multiply that by 3 hours. And what happens is the hours in the numerator and the hours in the denominator will divide out. And then 6 times 3 is 18. And then the units on this is going to be miles. So for part B, we have 18 miles. Okay, part C says, do you see a relationship between the previous answer and the graph? So it turns out that if I dropped this line down here, if I'm looking at this shape here, the shape that's formed is a rectangle, and it turns out that the 18 miles is also represented by the area of this rectangle, because this dimension here is 3, and this dimension here is 6. Although it doesn't look like it because the scales for the axes are different, but those are the correct dimensions. So for part C, we can say that the amount Mr. Kwon ran is also represented by the area underneath the horizontal line. And in parentheses, I'm just going to say which is our curve. So that horizontal line is a function. It just happens to be a constant function in this case. So in the next example, let's take a look at something where we're looking at something that is not a constant function. Example 3 says, the velocity graph of a braking car is shown. Use it to estimate the distance traveled by the car while the brakes are applied. So similarly, in our vertical axis here, we have that our vertical axis is velocity, but now we're measuring it in feet per second. And then our horizontal axis is measuring time in seconds. So just like in the previous example, we have velocity versus time. And it turns out that the distance traveled by the car is going to also be represented once again by the area underneath this curve. However, this time our curve is not constant, and so it's going to be a little bit more challenging for us to estimate the area, but we can still go ahead and try. So what I'm going to do is I'm going to break up my interval from 0 to 6 into smaller chunks. And I'm going to break it up into 1 second intervals. And if I do that, I can estimate the area underneath the curve in these 1 second intervals. And I'm essentially going to be creating a rectangle. Now, how high do I need to make my rectangle? Well, I think a good point to estimate it would probably be the middle of each, what we're going to call these subintervals. So from 0 to 1, the width of my rectangle is just going to be 1 unit. And I'm going to draw my rectangle with some height, and I'm going to stop kind of in the middle. So if we thought about this as a function, essentially that would be the output value if I plugged in 0.5. And so that's how I'm going to draw my rectangle. So it has a height there. And I'm just going to go ahead and do the same thing for the rest of my subintervals. So for this one, I'm going to say if I plugged in 1.5, it'd be about there. I'm just going to go ahead and draw this rectangle here. And then between 2 and 3 seconds, the middle of my rectangle would be about there or so. And then between 3 and 4 seconds, be about right there or so. And then the last one. Okay. The nice thing about trying to estimate the area under the curve this way using rectangles is a rectangle is a shape we know the area of. It's base times height. And another nice thing is we've dissected or split up our interval from 0 to 6 in a way where each of our subintervals has a base or width of 1 unit. So that has 1 unit, 1 unit, 1 unit, 1 unit, 1 unit, 1 unit. So when we're estimating the area under the curve, which in this case is estimating the distance traveled by the car, the area of my first rectangle, it's going to be 1 times the height. Now, I don't know exactly what the height is, and so this curve, if we thought about it as a function, I might call this curve v of t to represent the velocity function after time t seconds. So Now if I'm trying to estimate the distance, so estimated distance, it's basically us adding the areas of each of these rectangles up. So my first rectangle has a base or width of 1, and then I'm going to multiply it by v of 0.5, because that represents this y value, or this output value here. That would be v of 0.5. And then if I wanted to add the area of the next rectangle, it also has a width or base length of 1. Then its height would be v of exactly halfway here between 1 and 2 would be v of 1.5 plus 1 times v of 2.5. Hopefully you're seeing the pattern now. So 1 times v of 3.5 plus 1 times v of 4.5 plus 1 times v of 5.5. And that's going to be the height of our last rectangle. And hopefully you see that every rectangle or every term in our sum here is being multiplied by 1. And so if that were any other number, we could factor it out, and we could still factor it out, or we could just think about this as the velocities by themselves. So now what I'm going to do is I'm going to go ahead and estimate those, and your estimations might be slightly different than mine, but I'm just kind of eyeballing it. So v of 0.5 I can see is between 40 and 60, and it's a little bit closer to 60, so I'm just going to say maybe 57. And then we want to go ahead and do our next value, which is v of 1.5. v of 1.5 is like right here, and it's between 20 and 40, definitely much closer to 40. And so I might actually just eyeball it and make it 40. I think I drew it a little bit under 40, but 40 or 39 should be fine. And I'm just going to go ahead and fill in the rest of the values that I think I was able to eyeball for the output values of my velocity function. And so if we add up all those numbers together, this sums to 157. And we want to make sure we have units on this. And it asks us to estimate the distance traveled by the car. So in this case, we're measuring distance with feet. So it'd be 157 feet would be our final answer. Now, we're going to go more in depth into this notation later on, but I'm just going to introduce this notation now. So this 157 feet is an estimated value, and the notation that I want to give it is I want to label it with capital M and then a subscript of the number 6. So maybe pause the video and think about what are those two items coming from? Okay, so the capital M, we're using capital M because the way that we determine the heights of each of these rectangles is by using the middle value of each of our subintervals. So for example, between 3 and 4, the way that we got the height of our rectangle was by using the midpoint or middle value between 3 and 4, which was 3.5. And that's why we have this 3.5 here. So that's why we have a capital M for midpoint. And then 6 represents the number of subintervals that we have. So there's 1, 2, 3, 4, 5, 6 subintervals. And so that's why our subscript is 6.